University of Montreal, who's going to talk about symplectic homology and Viterbo's conjecture.
Thank you very much. I'd like to start by thanking the organizers for the possibility to present in this wonderful conference. I have been enjoying it very, very much so far. And one thing I must say related to the title of my talk is the following disclaimer. Disclaimer is that the number of the set of Viterbo's conjectures is, strictly greater than 1. And so the conjecture that I will talk about is related to the following easy fact. The easy fact is that if you have a, closed and connected Riemannian manifold and a smooth function, then you know that this number that I'm going to call gamma f, which is maximum minus minimum of the function, is bounded from above by, norm of differential times diameter. Right? And this can be reformulated as follows. If the graph of the differential of f, the Lagrangian graph, sits inside the unit cotangent bundle, so this is unit, maybe codisk bundle, then, well, this gamma f is bounded by some constant that depends on the metric. All right? Just as a somehow guiding example, let's look at a very simple case. So L is S1, which is R mod Z. And let's take the standard metric. Then this constant is 1/2. So diameter is 1/2. And this 1/2 is actually sharp because we can draw a nice picture. Okay. So nice picture is basically the following. So we know that unit codisk bundle is minus 1, 1 times S1, which I drew here. I don't know why I have a closed interval. I don't know. And then we can define the function by its graph, and by the graph of the differential. It will be something like this. Right, so and here we can make this area basically 1/2, and this area basically 1/2. And then max minus min will be this area, which is basically 1/2. Great. Now, the next observation, so this is a fact due to Viterbo, around 92, if I remember correctly, is that we can extend this gamma f, which, by the way, only depends on the graph of the differential, because, if you add a constant, nothing changes. Right? So we can extend it in the following way and write it as, let's say, gamma Lagrangian differential, comma L, where L will be somehow the zero section inside T star L. For a metric gamma on the Hamiltonian orbit of L. So on, let me call it maybe O of L, which is you take the compactly supported symplectomorphisms of T star L and apply them to the zero section. So it's all kind of these Hamiltonian deformations. And one nice thing to observe about this metric is that it is invariant under the action of the same group, right? So gamma, let's say phi L prime, phi L double prime is gamma L prime, L double prime for all, let's say, pairs in OL and all phi Hamiltonian diffeomorphisms like that. And another observation, well, it's somehow just kind of a feature, if you wish, of the construction, is that it depends on the choice of coefficients. So this is a coefficient field. Okay, so this is some sort of like a fancy nonlinear generalization of maximum minus minimum. And somehow, if one looks at this easy fact, one can immediately conjecture. Just a moment. So, coefficients, well, you see, this metric here depends on choice of coefficients. It is a homological minimax construction. I will review it in a certain way a bit later. But it comes from either generating function homology or Floer homology. Right? And then a priori it depends, we don't know. Right? So then if Viterbo conjecture the following, so if we have the Lagrangian equal to Tn and
can you remind me what C of G is that gamma f is
C
referring to?
of G, this one?
Yes.
In this case, it's just the diameter.
Okay, so would correspond to the right side.
Yeah. Yeah, so it is the diameter because, you know, this inclusion just means that norm is less than 1. This is a very interesting question because actually in a moment I will finish writing the conjecture, which states that if you have two Lagrangians, then yes, that sit inside the unit Codis bundle, then this distance is less than some constant depending on G, but also on K because everything depended on this choice of coefficients K. And one might think that this C will also be something like diameter. But actually, here is a little remark that in this case, even like if we fix one of them to be zero section, if L is S1, and somehow then what I will call C S1 of K, this constant, it must be at least 1. And the diameter was 1/2, so it's a different thing. And here's a way to see this. Now, instead of looking at the unit Codis bundle, I will look at Codis bundle of radius 2. Okay, so it will be minus 2 times S1. And there, as before, I have graph of my function, only I can scale it by 2, so then it will have this form. Right? Again, but with area basically 1, area basically 1. However, this does not sit inside the unit Codis bundle. Right? But we know that it is invariant under the Hamiltonian group. So we can do some slight modification. We can bend this part here and bend this part here. So we can do this and this. Okay, and then area is still 1 and area is still 1. And by invariance, we get that our gamma is basically 1. So you see it this way. And somehow a little second remark is that let's say L prime is inside the Hamiltonian orbit somehow where diffeomorphisms are supported in the codisk bundle is the same as saying that L prime is in the orbit inside the big cotangent bundle, and also L prime is inside the codisk bundle. Okay, so you can isotope either inside or outside, and the idea here is to use scaling by Liouville flow, exactly as Jorgos has explained to us before. All right, so of course, this inclusion is trivial, but the other inclusion, one has to make a little construction. Okay, now this conjecture is of course motivated by the easy fact, but it is motivated by other things as well. So the initial motivation came from Hamiltonian PD. More specifically, the notion of symplectic homogenization. It also implies certain structural results on the group of Hamiltonian diffeomorphisms supported in codisk bundle. So it basically immediately gives you a quasimorphism on the compactly supported Hamiltonian diffeomorphism group. And also it gives you a bunch of somehow C0 statements. So here is a little proposition. So here is a proposition. Viterbo conjecture for a pair LK implies the following. So if L inside M is a Lagrangian submanifold, and let's say that relative pi2 is 0. So for example, one can look at zero section inside a cotangent bundle. But there are other examples. And somehow L prime, L double prime are inside the Hamiltonian orbit of L. Then, if L double prime, let's say, is inside a small Liouville, Weinstein neighborhood of L prime, right? So it's kind of symplectamorphic to the radius R codisk bundle, and R is somehow sufficiently small, then the spectral norm, which can be defined in this case, will be less than R times this constant. Okay, so somehow it means and implies some sort of symplectic Hausdorff continuity of gamma and barcodes by our work with Asaf Kislev, et cetera, And perhaps another little remark that somehow this proposition is not the most general one can do. One can have a version with, let's say, L and M monotone with maybe some little additional assumptions. And this is how one proves C0 continuity of the Hamiltonian gamma for CPN using Viterbo conjecture. Right, so kind of works in larger generality. And another observation is that somehow, while this implies C0 continuity, when it works, it implies more because you can have two Lagrangians that are somehow very, very close to each other in this sense, in the sense of being contained in a small neighborhood. But one cannot obtain one from the other by C0 small Hamiltonian diffeomorphism, because there's kind of a lot of wiggles. Okay? All right. So I hope these motivations somehow make you wish that this conjecture were true. However, there are some difficulties. So, for example, same conjecture is false for similar settings. So not precisely for this setting, but when you start replacing some metric by another metric and so on and so on. So for example, it is false for the Lagrangian Hofer distance instead of gamma distance. So this is Khanevsky. It's false for well, other Liouville domains instead of D star L. So this is a very nice construction of Zapolsky. It is also false for somehow the Hamiltonian gamma on the compactly supported Hamiltonian diffeomorphism group. So this is Monsner, Visheri, and Zapolsky. And finally, it is also false in immersed version. So this is something I learned from Jorgos. Where is Jorgos? So actually, this construction is quite similar to this one, except that you don't stretch by 2 and bend, but you stretch by 1,000,000, then you bend, and then you wrap around. So then the gamma will be like 1,000,000, but of course, you will have to introduce self-intersection points. But okay, that's the immersed setting. All right. Okay, and
That's the trajectory for general Liouville domains, because there your constant depends on the measure.
absolutely.
Yeah, but how is the statement of the trajectory for general Liouville domains? You said it's wrong.
It is false. So I would not like to state it.
Trajectory is false for more general Liouville domains.
Yes. So you take a Lagrangian, you have a Lagrangian gamma norm on the Hamiltonian orbit of this Lagrangian, and if your Liouville domain is not D star L, if it's like a plumbing of 3 D star Ls already, then this metric will be unbounded. You can kind of start wrapping around in the other direction. So this is this very nice construction of Zapolsky. All right, and so somehow this is bad news. Good news is that in certain closed cases, there is a construction of Entov and Polterovich that does give some bound, and I will talk about this a little bit later. And finally, I must say that there were certain previous works of Viterbo and Buchowski. Humilier, Leclerc, and Sifadini that proved some very interesting results in the same direction. However, the conjecture has remained open for a while, and the main results of today are theorem 1 and theorem 2. So theorem 1 from 2018 is that conjecture is true for n equal to 1 and field F2. Okay, so for Tn for n equals 1, it's a circle. right? And it gives a bound on this S1 S1 kind of optimal upper bound of 2 in this case. And somehow the same is also true for certain other Lagrangian submanifolds than S1. So it is also true for L in certain compact rank 1 symmetric spaces. So RPN, CPN, HPN, and Sn, n greater than 1. Also, basically we'd have 2 coefficients, but I think so CPN can be done with any coefficients. One can see exactly how far one can extend it. Okay, so this is result 1, and its proof I will not discuss much. I will just say that somehow it uses the geometric structure that one can put on these spaces, namely Zoll metric. And then this allows you to compactify the unit codex bundle in a certain nice way, where you have the bounds coming from quantum product of J-holomorphic disks, and then you make some sort of quantitative decompactification process and obtain a kind of. That's a great question. I believe it is, but some student will do it. Okay. And here is theorem 2. So this one is from 2019. This one says that conjecture is true for all n and all k. And and it is also true for all L prime, L double prime in D star L exact. So you don't even need to be Hamiltonian as a topic to 0 section. Of course, if we know nearby Lagrangian conjecture is the same. It's believable, and it is also true for other pairs Lk. So for example, if K is F2 for a product of spheres, well, let's say positive dimension, or if K arbitrary, then products of even spheres. Odd spheres. Odd spheres. Right, so S1, S3, and so on. Okay. So this is the main result I'd like to talk about today that uses methods of symplectic cohomology. But somehow today, for simplicity of exposition, let's assume in theorem 2 that field is actually with 2 elements, and the 2 Lagrangians are actually isotopic.
Viterbo's continuity is only for torus?
Yes, so Viterbo conjectured it for torus, but of course you can interpret it for any Lagrangian. And then it might be true for some, might be false for some. We know no counterexamples. So, it would be nice to prove that there aren't any or to find one. Okay, and so now I would like to say some words about the proof. So somehow for the proof, I'd like to recall a little bit about the construction of gamma, at least in the setup of Lagrangian Floer theory. So L double prime, L prime are in the orbit, then by work of Floer, we know that first Floer homology of this pair is isomorphic to homology of L. And here, by the way, we kind of chose some coefficients, right, which were for our discussion F2, so I'm not worrying about anything. And furthermore, generators, so intersection points of action level less than T give us a filtered homology group, so under level T, and connecting maps. So maps, HF less than S to HF less than T. Maybe I'll call them pi ST, if we know that S is less than T. Okay, that commute in a suitable way. This is also called persistence model. However, today I just want to note that if we have a class in the homology that, let's say, is non-zero, to either will correspond by 0.1 another class in Floer homology of the pair. That will be also non-zero, because this is an isomorphism. And then we can define spectral invariant of this class like so. So it will be the infimum of levels alpha, such that alpha prime is in the image of HF less than alpha to HF, well, just HF, so it is infinity level. Right. Okay, and these are called spectral invariants. And Viterbau's spectral norm, in this case, is written as, well, spectral invariant of fundamental class minus spectral invariant of the point class. Incidentally, this is the maximal one and this is the minimal one for the spectral invariants. Also know that somehow action a priori is defined up to shift, but we don't care about it because we have difference. Okay, and it gives a metric, as I said before. Now, what would be the strategy of producing an upper bound on this thing? Yes? Oh. Let me think about that. There are examples when individual spectral invariants depend on the field. But gamma itself, I don't think I have. But I'm sure that one can think and find some counterexample. Yeah. Anyway, so there is basically a unique known strategy of producing an upper bound, which is one finds an operation. Well, let's maybe call it P from HF less than T to HF less than T plus some constant. So kind of this operation does not increase the action too much. Right? So for some positive constant, that is first of all compatible with all the pi st. And second of all, on the infinity level, we get a map from HF star to HF star. But of course, this is isomorphic to H star of L, and this is isomorphic to, again, to H star of L. And then we can ask that it sends point class to fundamental class. Okay? Okay, so once you have this, you're in very good shape. Because then you can prove an upper bound essentially immediately. So then you can write the following. You can write spectral invariant of L equal spectral invariant of P of the point class. All right? But by a condition, well, just by somehow the property that P does not shift the action too much, you immediately bound this in terms of C point plus exactly this constant. So then you win by taking point to the left. Okay? So modulo finding such an operation, we have a proof. Okay, and somehow remark that in the closed case, for example, you can take CPN sitting as a Lagrangian inside CPN times CPN, except that you switch the sign of the symplectic form on one of the factors. So in this case, we can use holomorphic disks. So we can use P equal product with suitable quantum product with a suitable quantum homology class. Lagrangian or absolute. And this has been discovered by Entov and Polterovich in 2003. And it is related to the notion of quasimorphisms, Calabi quasimorphisms, and so on. But of course, in the open case that we're considering here, product will not help, because products decrease homological degree. So if you start with point, you can end up either with point or with 0. So it will not go to fundamental class. So one has to do something else. And that something else will be an operation that is a bit different. So I guess this is a proposition. Okay. Maybe step 1. So the construction of Seidel and Solomon that we heard about in James's talk so can be upgraded so that any class in symplectic homology, let's say of degree k, which is not necessarily 1, with a representative, let's say, alpha. So this will be a symplectic core cycle with somehow action strictly less than some constant c. Get operation exactly satisfying property number 1 over there. So let's call it maybe phi sub a. from HF star L double prime L prime T to HF star L double prime L prime less than T plus C. Of course, you might note that now I'm writing star above and not below, but I'm defining the actions in such a way that the two are compatible under Poincare duality. Okay. Yes.
So this, in case of n-top motor, which is pseudo quantum homology, is that idempotent somehow?
Not quite, no.
What kind of probability does it have?
Well, so somehow, you know, Lagrangian Floer homology of this guy is the usual quantum homology of CPN, and you need an inverse of the point. Right, so then if you take A equal hyperplane class times quantum variable, I hope I'm not messing this up. If I am, please let me know. Then A quantum star point is exactly a fundamental class, which is the unit. Well, M is CPU. All right. It's right, yeah, because point is h to power n, and you multiply by h once again, you get Q inverse unit, so that's the Q. Somehow, in general, for monotone manifolds, the spectral norm is not always like this. So there's a different definition that one must give. But for CPN, it's still fine. This formula works. One has to be careful, but essentially this formula works for a given Hamiltonian. But then one has to take into account the effect of, you know, Sider elements, Hamiltonian monodromy, but it can be done, and it's fine. Okay, so we get an operation. Of course, it will satisfy property 1. By the way, another thing is that Seidel-Solomon construction works for equivariant Lagrangians. And equivariant means that the restriction map, the closed open map, goes to 0 in homology. Not all classes here go to 0, but you can always correct them by a class in the homology, just usual homology of D star L to make it equivariant, because projection always somehow goes that way. Okay, and proposition 2, or maybe step 2, is the following. So we have Viterbo isomorphism. Right, so of Viterbo, Abundandl and Schwarz, Solomon Weber, and Abu Zaid. We have symplectic homology of D star L or T star L. It doesn't really matter. By the way, when I write D star L, it means that somehow the way I choose actions, the way I choose the Hamiltonians, has to do with this particular domain, right? So I increase the Hamiltonians, the slope in a color of this thing, right? But when I stop caring about actions, I stop caring about whether it's a domain or anything. So this is isomorphic to the homology of the free loop space. And I chose F2 coefficients, so I don't need to say anything else. And Poincare duality. We also have this nice isomorphism, right? And again, F2, so I don't care about orientability. Then the infinity level of this FEA operation, so from HF star to HF star, can be calculated. So it corresponds to a certain map, let's call it maybe P sub A, from H star L to, again, H star L, only with a degree shift. This degree shift is quite interesting to notice. So it's this one. And somehow, you know, in homology of loop space, maybe it's kind of, formally speaking, it's a different class, maybe A prime, where A prime is inside homology of the loop space, and I kind of take this grating. Okay, so we know that in homology of loop space there are often classes of very high degree. So if degree is bigger than n or equal to, this increases degree instead of decreasing like usual intersection product does. So then we have a chance, okay, to get from point to fundamental class. So it's kind of like a wrong way Lister-Schneermann argument. Okay. So it corresponds to this map, and this map can be described explicitly using string topology. So explicitly described via string topology of Chas and Sullivan. Okay, so this PA, now I use A again, will be given as a composition of 3 maps, which I will spell out just a little bit now. So it's kind of the composition as follows. H star L goes to H star free loop space L, goes to H star plus A, degree A minus n plus 1 free loop space, and goes back to H star L. Okay, so the first and the last maps are pretty easy. So this iota is inclusion of constant loops. Right, so each loop, each point you consider as a loop that's fixed at this point. The last one is evaluation. So it is evaluation at, let's say, 0 in S1. Right, so I did not say, so free loop space is kind of space of maps from S1 to L, and S1 has a 0. You can evaluate at the 0. All right? Of course, someone might say that the smoothness is kind of strange, but okay, you can choose various smoothnesses. Okay. All right, and the tricky map is this one. So this is M sub A, and this is a string bracket. So string bracket with A, and so kind of M A of B is bracket B A, which is given by, well, in various ways, but for example, is given in terms of BV operator and Chas-Sullivan product as so. I ignore signs because I actually work over F2 now, but you can put the correct signs. It's not a big deal. So here, delta is the Batalin-Vilkaevsky operator, and the star is the Chas-Sullivan product. Okay. Perhaps just to give an intuition for these two operators, let me write this down. I'm not sure what I'm doing. For delta, what you do is you take somehow, this is, of course, intuition. Rigorous construction is more complicated, but you basically take a cycle to the loop space, and then you construct a new, so this is a cycle, maybe like J cycle. From this one, you construct a new cycle, so this will be a J plus 1 cycle, which is, well, from K times S1 to our loop space, which suspends the S1 action, right? So maybe delta C K theta, where K is on K and theta is in S1. Well, this is a certain loop, so I can say what it is at T in S1. And this will be C of K at point T minus theta. Right, so this suspends the S1 action. And star is a product. So if we have, let's say, C1 and C2, which is a, well, K cycle and L cycle. To this, I associate C1 times C2, which is a K plus L minus N cycle. No, I guess I will erase this. Right, from K1 over LK2 to the loop space, where, you know, K1 is the domain of C1, K2 is the domain of C2, and K1 over LK2 will be basically points K1, K2 in K1 and K2, such that their evaluations agree. So C1, K1 equal evaluation C2, K2. All right, so in this case, we look only at loops of this kind that start at the same point, and then we can concatenate. All right, and this gives you a new loop, and this is the loop that you want here. Okay, so that's it. And finally, combining step 1 and step 2 that I have just described, we sometimes get exactly that point is sent to fundamental class. So for this, let's make a definition. So definition. L is a string point invertible. Well, over a field K, which in this talk is, of course, with 2 elements, but you can make the definition in general, and it somehow applies in the same way. If there exist maybe AN until A1 classes and homology of a loop space, such that the product of the associated operators, exactly like there, one, sends sends point 2. Right, and then somehow a corollary is that if LK is string point invertible, then Viterbo conjecture holds for LK. Okay, so this is a condition, and finally, one can give examples by using calculations in string topology. So for example, one can prove the following algebraic statement. So if L1 and L2 are string point invertible over K, then so is their product. And I guess a fact this is calculations in string topology, which is each odd sphere is a string point invertible over all K, and even sphere, each even sphere is string point invertible over field of characteristic 2, for example, F2. And this way we get that Tn is string point invertible over all K. Okay, so this concludes the proof, at least of theorem 2. And as a bonus, one can ask the following and answer. So somehow remark. Recall that by observation regarding this bending construction, we knew that C S1 with some coefficients is at least 1, and theorem 2 implies that the CS1 is less than 2. So we know that it is in this interval, the sharp bound. And then the question is whether is it 1, is it 2, is it 1.5? And somehow optimizing the constant C in the construction, in the proof. Sorry, theorem 1 here. Sorry. So optimizing constant C in the proof of theorem 2, we get that actually C of S1K is 1 for all K. So one can determine the classical, the optimal bound. And finally, I'd like to end with some discussion of other computations. It is a curious remark that most compact rank 1 symmetric spaces, as I have described, for which theorem 1 works, by calculations of Oancha and others, are not string point invertible over any K. So in a certain way, these two theorems are complementary. In fact, one can say precisely for which coefficients and which ones are string point invertible. And another thing is that if K is the field of, let's say, rational numbers or some other field of characteristic 0, then also basically compact connected Lie groups are good because you care about rational homotopy type. All right, and finally, I must say that for surfaces of higher genus or hyperbolic manifolds, closed hyperbolic manifolds, this string point invertibility basically never applies. So it would be fantastic to find a counterexample in those cases. All right, I think I will stop here, so thank you very much for your attention.